54. Identical charges Q equals 5 microcoulombs are placed at opposite corners of a square that has sides of length 8 centimeters. So we've got a square, this beautiful square. That's a really ugly square, actually. We got a charge here. We got a charge here. They are 5 microcoulombs each. And the lengths of my square sides are 8 centimeters. Point A is at one of the empty corners. So this is point A. And point B is at the center. So here. What is, okay. A charge Q0 equals minus 3 microcoulombs is placed at point A and moves along the diagonal of the square to point B. So minus 3 microcoulombs goes this way. What is the magnitude of the net electric force on Q0 when it is at point A? Is part A. Okay, so when we're here at point A, we have a negative 3 microcoulomb charge. This is a positive charge up here, so he's going to feel an attractive force that way. And this is a positive charge over here, so he's going to feel an attractive force that way. So the force between 2 point charges is KQQ over R squared, R hat. So for this charge, we have 8, that is not what K is, 9 times 10 to the 9 newtons meters squared per coulombs squared, I don't remember, times charge 1, which is 5 times 10 to the minus 6 coulombs, times charge 2, which is 3 times 10 to the negative 6 coulombs. Because these are vectors, I'm going to worry about the plus and minus signs later. Distance between here and here is 8 centimeters, so 0.08 meters squared. So if I punch that into this handy dandy calculator that doesn't belong to me, and if you know who Michelle Zhang is, let me know. Because I still have her calculator. And it's going to be mine, unless somebody finds her. Oh my god, what did I do? Ah! I broke it! Okay, we're going to try this again. On. Okay, phew. Calculators are hard, y'all. Times 10 to the minus 6 times 3 times 10 to the minus 6 divided by 0.08. That is not an 8 squared. So my force from this guy is 21.09 newtons. And this one is pointing up, so that is positive J hat. And hey, guess what? These are the same magnitude and the same distance apart. So they have the same force. Just this one is in the positive I hat direction. Okay, so our total force, we have an I and we have a J. So we got a Pythagorean Theorem, this baby. So that's my I hat plus my J hat squared. So squared, and then there's 2 of them, and then square root that. So my total force is 29.83 newtons, and that you can either write as, what is it, x plus y, or 29.83 newtons I hat plus J hat, or 29.83 newtons, and theta is 45 degrees. Either one of those is an acceptable answer. Yeah. All right, B. Part B. What is the magnitude of the net electric force on Q naught when it is at point B? So now we're here. My little negative charge is being attracted towards this guy. And my little negative charge is being attracted towards this guy. These magnitudes and these distances are equal. So hey, guess what? These are equal but opposite, which means that they're canceling out. So without doing any work, the force on that dude is 0. Huzzah. Pictures, they're your best friend. C. How much work does the electric force do on Q naught during its motion from A to B? Is this work positive or negative? When it goes from A to B, does Q naught move to higher potential or to lower potential? All right. So for each charge, we know that the work from A to B is equal to the potential energy at A minus the potential energy at B, which is Q times the potential at A minus Q times the potential at B. Since we eventually want to find the potential and talk about the potential, I'm going to use the lazy way, and it's going to be great. We're going to save some time. It's going to be awesome. Alright, so Q is my little baby charge who's just chilling, the one that's moving. That's our minus 3 microcoulombs. My potential at point A, I have two dudes contributing. I got this guy and I have this guy. The potential for each guy is KQ over R. Now, the distance is the same and the charge is the same. Direction does not matter for potential. It's not a vector, it's a scalar. So I just slap a 2 in front of there. Huzzah, because they're equal. RA. And at point B, same thing, KQ over RB. And there's 2 of them because they're equal. So if I stuff in my happy little numbers, we got 2 K's and Q's. I'm going to pull all those out too. Times 2 times 9 times 10 to the 9. And then meters squared per coulomb times Q of my dudes, which is 5. Times 10 to the minus 6 coulombs. 1 over RA. So RA is our 8 centimeters, 0.08 meters. And RB is this distance, which is 4 root 2. 4 root 2. Yeah, okay, 4 times root 2. So 0.04 root 2. Alrighty. So plug this into our handy dandy calculator. That doesn't belong to me. It belongs to Michelle Zhang, if you know who she is, so have her shit. Alright, minus 3 times 10 to the minus 6 times 9 times 10 to the 9 times 5 times 10 to the minus 6 times parentheses 1 over 0.08 minus parentheses 1 over more parentheses 0.04 times square root of 2. Oh god, what? No, back. Parentheses. Okay, so my work done is 1.4 joules. That is a positive number. Alright, so that's a positive number, which means that the potential energy at point A is greater than the potential energy at point B. Alright, so if we look at our potential energy is KQQ over R, which is Q times our potential, right? So from our work, UA minus UB is equal to our work. So UA is bigger because we left with positive work. So we have higher potential energy here. So higher potential energy. However, since our charge is negative, that means a higher potential energy is going to be a less negative number, so a smaller potential. So our dude is moving towards higher potential because he's negative. He likes to go to high potentials. So to higher potential. And here, we'll draw a picture. Pictures are nice. All right, so here's our original. So UA, we said was greater than UB because our work was positive, right? So UA is Q times VA, and UB is Q times VB, right? Q is a negative number. Negative number, VA. So, as I'm moving from here to here, my potential energy is decreasing, but I'm getting more negative. So negative is already taken into account, which means this is bigger. I'm getting more negative because I'm going to a lower potential energy. But because my charge is negative, that means that the potential is bigger.